All right, I think the final example I'm going to work for you today deals with something that's quite close to home and is kind of ironic. This is number 35, which, by the way, I picked way back in October. I did not add this problem recently, though it actually has real applications to our lives right now. Epidemiologists have found a new communicable disease running rampant in College Station, Texas. They estimate that T days after the disease is first observed in the community, the percent of the population infected by the disease is approximated by P of T is 20 T cubed minus T to the fourth all over 1,000 for time 20 days or less. We want to know how many days it takes for the percent of the population infected to reach a maximum, and we then want to know what the actual maximum percent of the population infected actually is. Even though this looks like a rational function, it's actually polynomial because there is no variable in the denominator. So I'm going to actually start off by writing this function in polynomial form. 20 over 1,000 t cubed minus 1/1000th t to the fourth. I know I could reduce 20 over 1,000. I'm not going to worry about that because I will have to reduce after I apply the power rule anyway. So I'm going to start now by finding the first derivative. 60 over 1,000 t squared minus 4 over 1,000 t cubed. Now I'm going to go ahead and reduce 0.06 t squared minus 4 thousandths t cubed. This is what the first derivative equals. Now, while we'd love to say there's going to be a minimum value, we are going to assume that there's some local maximum in this problem somewhere. When a local maximum occurs, that's when the first derivative is equal to 0. This is cubic, but this is a solvable cubic function, or cubic equation. Add 0.004 t cubed to both sides, then divide both sides by 0.0. No, let me back up. I'm going to divide both sides by t squared first, and then divide both sides by 0.004. There we go. That gives us a value of 15. Now, similar to what we did on Monday, we're going to evaluate the original function. For this problem, unlike the previous examples where we had no evaluations of endpoints in the domain, here we actually have endpoints of the domain, 0 and 20. We want to know, will 0 or 20 days lead to a larger value or larger percentage of the population infected? With the fencing problem, we didn't need to do that because if the endpoint was one side of a fence, it wouldn't be a rectangular fence. So, long story short, we need to do the following evaluations. P of 0, P of 15, P of 20. P of 0 is easy, 0. P of 15, I should actually give myself a little bit more space here. P of 15 is 20 times 15 cubed minus 15 to the fourth over 1,000. So 20 times 15 cubed minus 15 to the fourth. Divide that by 1,000, and I get that the percentage of the population that is infected in 15 days is 16.875%. Now P of 20, 20 times 20 cubed minus 20 to the fourth over 1,000. Well, 20 times 20 cubed is 20 to the fourth. 20 to the fourth minus 20 to the fourth is 0. So, lo and behold, the right endpoint is a sudden drop-off in the percentage of infected population. So the question asked, after how many days was the percentage of the population infected a maximum? 15 days is the max, and 16.875% is the max value itself, the actual maximum percentage of the population that has been infected. All right, these are just a few examples of what to do. When in doubt, take the first derivative, solve the first derivative set equal to 0, and that will give you the critical value. Then evaluate that number in the original function, and when you have known endpoints within the domain, evaluate those. Whichever gives you the largest or smallest will be the maximum or minimum that you are looking for in the problem.